I'll be talking about process convergence of the quick select residual, and I'll first introduce quick select again. So quick select is an algorithm to solve following problem. We have n values, u1 to un, then we are given the value k, and now we want to find the element of rank k, or just in other words, the kth biggest element, or in other words, the element such that there are k elements that are a bit smaller than that. A normal computer scientist would just sort all of these values and then take the kth one. That would take n log n time, but we can get to O(n) time if we use quick select, and it's a kind of variant of quick sort, and that's how it works. Let's say we have these 8 values and we want to have the 4th biggest one. Then, like quick sort, we would just take the first value and compare everything with it, the 6. And we find out we have 5 values that are smaller, 2 values that are bigger. That means 6 is the 6th biggest value, and we want to have a smaller value. So we go into the left set and fix our new value to compare with. This value is called pivot. And now we have 2 values that are smaller, 2 values that are bigger. We see 3 is the 3rd biggest. So we go into right set, compare again. And now we have that 4 is indeed the 4th biggest value. And that's how quick select works. Okay. To analyze this, we have to choose a random model. And we just say that the u1 to un are independent. We could, in reality, use any distribution, but uniform 1, 0, 1 will make our life easier. And what we want to consider first is the amount of comparisons that we have to do in each step. So the last input that we have to choose is the rank, and there we have different choices that we can do. One popular choice is a fixed rank, or just make the rank also random and choose it uniformly. But what we want to look at is to look at the rank t times n floored for some fraction t. That is basically what you have to do if you want to have the empirical t quantile, because this would be the rank of the quantile, and that's why it's called quick quant process. And if we write stn for the amount of comparisons to find this rank tn, to find this t quantile, then we know that stn divided by n converges to for n to infinity to some limit st. And we can easily visualize this limit like this. So for the first step, everything has to be compared once. So 1 for everything. And then we split it up, and the left part gets compared with everything in the left part, the right part gets compared with everything in the right part, so we get squares, and each of the squares is then split again into another square at a uniform place, and so on, and so on, and so on. And as you see, the squares are getting smaller, they're getting geometrically smaller, so this thing converges, and might also look like this, or this, or this. Okay. So, but this we already knew. So the question was, what happens if we subtract this limit and rescale? We kind of, we call this residual, and we kind of thought it must be normal, and it indeed is normal. So I skipped the preliminaries, so this is a bit strange maybe. So we write fn for the empirical distribution function of u1 to un. So that's a random variable. So then we say the residual process is this term, the costs at step t, to compare t, minus n times the limit, but not at t, but rather at the inverse of the empirical distribution function of t. Then we scaled it with square root of n, and this converges then to a limit process, which we call g infinity. It converges on d01 in this cohort metric, and this limit is a mixed-centered Gaussian process. And I guess now I have to explain what d01 is, why we have an empirical distribution function here and not just the limit itself, and what the covariances of this Gaussian process are. Okay, first, some reminder about why we care about d01, why we look at the process. So if we study the process, we can consider all choices of rank simultaneously. You see there are many times to choose the rank. And if we choose the rank, then the amount of comparisons like for a fixed point or for a random point can be written just as functions of, well, this function t to stn or t to gtn. And these functions are usually continuous. And then we have this theorem in probability, which states that if we have convergence in distribution, we also get convergence in distribution for the function values, as long as the limit is not at a discontinuity of this process, of this limit. And that's the case for fixed or random points. So this means that if we have process conversions, we also have conversions at fixed and random points or for the maximum. And I already said that STN converges to ST. This is also as process. So for STN, it's already known. So the space D01 that those processes live on is defined as follows. STN is a right continuous step function. If t is a 1, it jumps at every multiple of 1 over n. And functions that are right continuous and have left limits are called Cadillac of the French. And we call this space where they live on D01. And for measurability, we need a metric that is different to the uniform metric. And this is called Skorodt metric, because these jumps have to be, because we have to account for the case that jumps are not exactly at the same place. To do this, we need a monotonously growing bijection. This will serve as a time shift to align our jumps. And then we define the Skorodt metric as whatever is bigger, either the distance between the functions after we shifted one of them with lambda, or the distance between lambda and the identity, and we can choose just the lambda such that this entire term is minimal. And as you see, the first term shows that the Skorodt metric is always smaller or equal than the uniform norm. And the second term can be seen is the time shift. For example, if we have a jump at some point A and a jump at some point B, these functions are, the distance between these functions is just the distance between B and A, because we can find a bijection that maps A to B, and this distance would be B minus A. Okay, so this is the space, this was the space where we would want convergence on, and now we have to look again at how quick select really works. So in the first step, let's say we have this whole interval where the values are on, and now somewhere on this interval is the first pivot. The pivot splits element into left and right, and for the left elements we find a new pivot, and for the right elements we find a new pivot. And now if we have some value alpha in it, we see that the values that alpha, in the first step, alpha goes into this interval, in the second step into this interval, and then we would get new pivots and smaller intervals, steps of intervals there. And you can see that these intervals are exactly where other values are that alpha is compared with. So if we had to rank, we could not really see in which interval we are going. So, but if we have the result alpha, we always see, we can see in which interval we are going. So we should have really indexed with alpha, and alpha is given from u1 to un just as the inverse empirical distribution function of t. So we now write S alpha n for basically the same thing as STN, the costs to compare and find value alpha when we have n values. So because this is basically like as we are looking for value alpha, this is called the quick val process, and it turns up because it's much easier to describe than this quick quant process. Okay, so step, okay. As in you have to do multiple. You can also do something for that. It's really just the time shift of the old process, of the STN process. Okay, so if we want to analyze it stepwise, we write S alpha Kn for the amount of comparisons we have to do in step K. And we see that all of the elements that we have in step K are the elements that fall into the same interval as alpha, as this into this interval I alpha K. And if we now condition on the pivots, that is conditioning on where the intervals now lie, we have that S alpha Kn is almost binomially distributed, but we have some error that we make because we conditioned on the pivots. So we have an error that is until some, in step K, we have had K pivots until now. So we have made an error of order OK. So let's write tentatively S alpha Kn is binomial plus some error. And this explains where our limit comes from. Because on the stepwise level, we see a binomial distribution scaled by n should converge against its probability, and its probability is I alpha Kn. Now, if we can bound this sum, we see that the sum over all steps should then also be converging against the sum of all these probabilities. And indeed, this is how our limit process looks like. And this convergence was shown to be almost surely, to hold almost surely, and in L2. And these were results contained in some papers from Phil with Nakama and with Natara. And if we now turn to a residual process, we see that, again, on the stepwise level, if we subtract this mean, we get convergence against the normal with I alpha Kn minus I alpha K squared as the variance. Again, if we sum up over all steps, we should also get a normal if it converges. And if we want to look at how this variance looks like, we have to also consider the covariances between two different steps. That is, the covariances of an element being in I alpha K and being in I alpha L for a smaller interval I alpha L. But because those intervals contain each other, we see that the product here is just I alpha, whatever is bigger, K or L, the smaller interval, minus the product of the interval lengths. And if we sum this up, we get the residual, the variances of the residual. And if we want to have the same for covariances, we would have to do a bit more with NOR notation. So you see, we have two values alpha and beta, and at some point we get a pivot in between of them, and then we split them into different paths. And from this point on, all of the intervals are disjunct, and above this, all of the intervals are equal. So if we want to know if they are actually in the same interval, then one of them, the one in the smaller step, must contain both alpha and beta. So it must be before this branching point, and the element must be in the smaller interval. But well, writing it like this is a bit tedious. So we just say, well, we know these are not only interval lengths, they are real intervals. So let's just write this for the length of the intersection. I know these are lengths and not intervals, but who cares? So then we can write the covariances much more easily just by writing length of intersection minus product of the interval length. And now we have everything that we need to write our main theorem in a better form. That is, the following. Now we define our residual process not with STN, not with quick quant, but rather with quick val. And as you see, this scaling factor then vanishes of the empirical distribution function, and we directly get convergence against the limit. And now we can also say what the covariances are. They are just what we calculated on the last slide, the length of the intersection minus the product of the lengths. And yes, just to give a small intuition of how to prove this would be, again, stepwise. We know we can just partition those steps into early steps, middle level steps, and late steps. Okay, for the first steps, we see if we have a fixed k, then we have only chosen 2 to the k different pivots. So we only have 2 to the k many different values. And for them, we can use the multivariate central limit theorem. And as we increase k, these intervals are always getting smaller. So these values are usually very small and have few elements. So for the middle, we can use Chernoff. And the last part, you see this 4.5 log n. As you might know, tree behind quick select is a binary search tree, and this is a log tree. So its height is only of order log n. So actually, we don't have any elements here. S alpha kn is just empty. And we just have to discount for the term that's here, the I alpha kn, but I alpha kn is just falling geometrically and fast enough. Okay. Until now, this was comparisons. And as another application, we wanted to consider other cost measures. So you see, in each step of quick select, we compare everything, and then we sort into smaller and bigger elements. And the sorting is usually done in place. That means that we have to swap elements around, swap smaller elements to the left, bigger elements to the right. And swapping can be considerably more time intensive than comparing. Let's say because we have in different on memory. And for swapping, one usually considers 2 schemes, the Ho scheme and the easier Lomuto scheme. Let's start with this Lomuto scheme. Let's say these now brown looking elements are the smaller ones that we have to get onto the left side. So for Lomuto, we start on the right side, and whenever we find a smaller element, we shift it to the right side. So here, this one got shifted to the left. Then the next smaller element is this one. It also gets shifted to the left, but we didn't see that on the left side there was actually a smaller element. So we get another smaller element here. Then we shift it, swap it, and then we see all of those are already swapped elements, and we are finished. But because Lomuto has to swap every smaller element to the left side, its cost is the amount of smaller elements. And a bit more intelligent is the Ho scheme, which starts from both sides at once. It looks for smaller elements on the right side, bigger elements on the left side, swaps them, does this again, and you see it only needs two steps. And well, it's just amount of elements that are on the wrong side. So smaller elements on the right side, respective bigger elements on the left side. And if you condition on how many smaller elements you have and how many elements you have, it's just hypergeometric, hypergeometrically distributed. And that means that for both Lomuto and for Ho, this amount of swaps that we do in each step is asymptotically for big N normal. And it's centered around some mean W alpha K. Let's say it's not really the mean because it's actually the conditional expectation from the interval sizes, but we can do the same as for comparisons. And we see that we can do the same, define the same residual process. And this residual process then converges in the same way as for the comparisons against the mixed-centered Gaussian process. on this space of Cadillac functions, and this holds for both schemes with different covariance of functions. But I won't write them there, way too long. And the second thing is, how about the comparison cost not being 1? So our other model is that comparison times depend on the length of on the items that are compared. For example, if you have 2 strings that have the first character different, you only need to look at the first character to compare them. If they have 100 characters in common at the front, you have to check all of those 100 characters to see which one comes first. So, and the same holds for decimals that are very close. So if we not look at the comparison time as one constant, but rather at how many bits you have to compare, then you see that typically closer elements take longer to compare.
Why?
Because
they've got a prefix with some magic length. Because you're dealing with the analysis, not with the algorithm.
What prefix of made? Why?
If you know the prefix of all the elements on where you were going, like say, and if you're concerned with that with long strings, it's worth doing.
Yes.
Having figured that out, then.
But if you're really concerned about it, I think you would use something like tries or some try-like scheme. I think.
A little rugged. I mean, the question is whether you use trig selector or not. That's a
yes.
yes. And there are issues with lower bounds, and that's where I'm sort of coming from.
Ah, yes. So, well, you could cache them, I guess, but still have. You wouldn't have a pivot that has this prefix and then all z's. So you would typically have values that don't have the same prefix where you're comparing in each. So I guess kind of makes sense to consider this, but I don't know. So let's say we have some cost function beta to compare a pivot u to v. And now if v is uniformly distributed on 0, 1, let's say just a random item, then we have to bound this beta. We say beta is epsilon tame for some epsilon bigger than 0. If for any bound x0, x bigger than 0, the probability to compare some fixed pivot u to some random value v to be bigger than x is falling polynomially with epsilon inverse. That's usually it's just sufficient to use Markov bounds and say that beta uv has an epsilon inverse moment, and this moment is uniformly bounded in u. So if I say epsilon has to be smaller than 1/2, that means we have more than half second moments. And this usually covers the bit comparisons. Let's say you have strings with independent characters or something like that. Then you usually have that beta uv has exponential tails. You won't get elements that are that hard to compare. And we can define the residual as usual, the same with the same limit process. And then we see what Matera showed is if beta is epsilon tame for epsilon smaller than 1/2, the residual converges at a fixed point. So if we don't look at process, we need a bit more than second moments. And what we then showed for betas that have more than 4th moments, then that also the residual process converges as a process. Okay. That was my talk. Thank you so much.
Are there any questions? We already had a few during the talk. Yeah. Where's Conrado? Coming.
Hi, just one question. Is the techniques, are the techniques that you have used here also applicable when you are studying something that's not linear, let's say the number of recursive steps in the algorithm, for instance? So you're analyzing quantities like comparisons and swaps, and you'll have a linear number of those on each recursive step. What happens if your quantities, the quantity that you're analyzing is not linear?
Ah.
Do the techniques apply in that case?
Linear in and kind of hard to see because I think I never thought about it, because in all of those examples there was the straightforward let's go here, there was this straightforward stepwise normality, stepwise asymptotically normality, and we just haven't thought of a good use case where it wasn't linear, but we still had some stepwise things to consider. So.
I have a comment and a question. The comment is that it's very nice to see Jason Matter's dissertation work come to even greater fruition here. Also, the question is this: could you take things one step further and get joint convergence of the number of comparisons and the number of swaps, rather than treating each separately?
Yeah, I think it's definitely possible, because on this level, these conversions are jointly, and then basically we use these convergences and Slutsky or something like that. So I guess it should be possible.
I think so too.
It's a nice idea for expansion.
It would be interesting to see what sort of correlation there is between the number of comparisons and the number of swaps.
That should be known. I guess I've already seen this level stepwise. Okay. Yes. Thank you.
One more question.
Alex needs more, Sebastian needs more exercise.
Downwards is fine. Okay, now I had to come back eventually anyways. So you keep this for your answer.
Everything goes through in a straightforward manner if you use some median of 3, median of 5 approaches.
And
Does that make sense to everybody else?
There's one problem, and this is this step here, because in this step, basically saying that I alpha k, we can say that I alpha k is falling with some factor of 2/3 squared, which comes from its moments, and then we compare this with this 4.5 log n, which basically comes from the height of the height of a binary search tree. So
sorry, I don't get the height of the binary search tree. This is an expected value, and it's almost and according to him, it's almost certainly less than 3.
Yes,
according to Luke.
I guess it was 4.3. Yes.
Sorry.
4.310, and I originally so 4.5 is just, and it's
natural log.
It's 4.5 times the log n. So it's actually 4.3 something, and
I was
its
speaking
variance
binary.
is of order O, and its variance is its variance is of lower order than log n. I get the word constant. So the problem would be to get for other split trees, as you said, 3 median and 5 median, to get
Sure.
some similar bounds for the height.
You're just
To
great.
just
And also,
that.
thank you for helping me sort out why it's 4.5 rather than 3, because it's the base of the log. Fine. And this will have nothing to do with any higher moments, no, of Floyd and Rivest median.
What?
Floyd Rivest median algorithm. You take a random sample of size something.
Okay.
Let something be marginally bigger than square root of n for technical, ultimately, when you do the analysis.
Mm-hmm.
Then you say, you're looking for the median. So you take somebody that's guaranteed, that's highly likely to be a tad below the median and highly likely to be a tad above the median from the sample, play the games right, and there you go, compare left, and with probability virtually half, you compare right,
Yes.
and now you've got a very small sample. But the high moments are going to be tiny.
I think this one, I think there was a paper from Sulzbach about this, and because in this case we are really always splitting at 1/2, at least if n is large.
Yeah.
So in this case, it more looks like it really looks more like the selection of radix sort, radix select. I think it's radix select, where it really split in at half at every step.
Or wherever you're looking for.
So in this case, this limit is not, this limit here is not random. It's just always 2 to the minus k. And this was already done before for these kinds of algorithms.